Section 5.2 Probability Rules. Learning Targets. By the end of the section, you should be able to give a probability model for a random process with equally likely outcomes and use it to find the probability of an event. Use basic probability rules, including the complement rule and the addition rule for mutually exclusive events. Use a two-way table or Venn diagram to model a random process and calculate probabilities involving two events. Apply the general addition rule to calculate probabilities. The idea of probability rests on the fact that random behavior is predictable in the long run. In Section 5.1, we used simulation to imitate a random process. Do we always need to repeat a random process? Tossing coins, rolling dice, drawing slips from a hat, many times to determine the probability of a particular outcome? Fortunately, the answer is no. Probability models. In Chapter 2, we saw that a normal density curve could be used to model some distributions of quantitative data. In Chapter 3, we modeled linear relationships between two quantitative variables with a least squares regression line. Now we're ready to develop a model for random behavior. Many board games involve rolling dice. Imagine rolling two fair, six-sided dice, one that's red and one that's blue. How do we develop a probability model for this random process? Figure 5.2 displays the sample space of 36 possible outcomes. Because the dice are fair, each of these outcomes will be equally likely and have probability 1/36. Definition: probability model, sample space. A probability model is a description of some random process that consists of two parts: a list of all possible outcomes and the probability for each outcome. The list of all possible outcomes is called the sample space. A sample space can be very simple or very complex. If we toss a coin once, there are only two possible outcomes in the sample space: heads and tails. When Gallup takes a random sample of 1,523 U.S. adults and asks a survey question, the sample space consists of all possible sets of responses from 1,523 of the over 240 million adults in the country. A probability model does more than just assign a probability to each outcome. It allows us to find the probability of an event. Definition: event. An event is any collection of outcomes from some random process. Events are usually designated by capital letters like A, B, C, and so on. For rolling two six-sided dice, we can define event A as getting a sum of 5. We write the probability of event A as PA, or P sum is 5. It is fairly easy to find the probability of an event in the case of equally likely outcomes. There are 4 outcomes in event A. The probability that event A occurs is therefore PA, number of outcomes with sum of 5 over total number of outcomes. When rolling 2 dice, 436, a sheer 0.111. Finding probabilities. Equally likely outcomes. If all outcomes in the sample space are equally likely, the probability that event A occurs can be found using the formula PA, number of outcomes in event A, over total number of outcomes in sample space. Example: spin the spinner. Probability models. Equally likely outcomes. Problem: a spinner has 3 equal sections: red, blue, and yellow. Suppose you spin the spinner 2 times. A. Give a probability model for this random process. B. Define event A as spinning blue at least once. Find P of A. Solution: A. Sample space: RR, RB, RY, BR, BB, BY, YR, YB, YY. Because the spinner has equal sections, each of these outcomes will be equally likely and have probability 1/9. B. There are 5 outcomes with at least one blue: RB, BR, BB, BY, YB. So, P of A equals 5, divided by 9 equals 0.556. Basic probability rules. Our work so far suggests 3 common sense rules that a valid probability model must obey. 1. If all outcomes in the sample space are equally likely, the probability that event A occurs is PA equals the number of outcomes in event A over the total number of outcomes in sample space. 2. The probability of any event is a number between 0 and 1. This rule follows from the definition of probability in section 5.1. The proportion of times the event would occur in many trials of the random process. A proportion is a number between 0 and 1, so any probability is also a number between 0 and 1. 3. All possible outcomes together must have probabilities that add up to 1. Because some outcome must occur on every trial of a random process, the sum of the probabilities for all possible outcomes must be exactly 1. Here's another rule that follows from the previous two. 4. The probability that an event does not occur is 1 minus the probability that the event does occur. If an event occurs in, say, 70% of all trials, it fails to occur in the other 30%. The probability that an event occurs and the probability that it does not occur always add to 100% or 1. Earlier, we found that the probability of getting a sum of 5 when rolling 2 fair 6-sided dice is 436. What's the probability that the sum is not 5? P sum is not 5 equals 1 minus. P sum is 5 equals 1 minus 4. 36 equals 32 divided by 36 equals 0.889. We refer to the event not A as the complement of A and denote it by AC. For that reason, this handy result is known as the complement rule. Using the complement rule in this setting is much easier than counting all 32 possible ways to get a sum that isn't 5. Definition. Complement rule, complement. The complement rule says that P of AC is equal to 1 minus P of A. AC is the complement of event A. That is, the event that A does not occur. Let's consider one more event involving the random process of rolling 2 fair 6-sided dice, getting a sum of 6. The outcomes in this event are 1, 5, 2, 4, 3, 3, 4, 2, 5.1. So P sum is 6 equals 5/36. What's the probability that we get a sum of 5 or a sum of 6? P sum is 5 or sum is 6. Char P sum is 5 plus P sum is 6. Char 436 plus 536. 936 equals 0.25. Why does this formula work? Because the events getting a sum of 5 and getting a sum of 6 have no outcomes in common. That is, they can't both happen at the same time. We say that these two events are mutually exclusive, disjoint. As a result, this intuitive formula is known as the addition rule for mutually exclusive events. Definition. Mutually exclusive disjoint. Addition rule for mutually exclusive events. Two events A and B are mutually exclusive, disjoint, if they have no outcomes in common, and so can never occur together. That is, if PA and B equals 0. The addition rule for mutually exclusive events A and B says that PA or B, PA plus PB. Note that this rule works only for mutually exclusive events. We will soon develop a more general rule for finding PA or B that works for any two events. We can summarize the basic probability rules more concisely in symbolic form. Basic probability rules. For any event A, 0 less than or equal to P of A less than or equal to 1. If S is the sample space in a probability model, P of S equals 1. In the case of equally likely outcomes, PA equals number of outcomes in event A over total number of outcomes in sample space. Complement rule, P of AC equals 1 minus P of A. Addition rule for mutually exclusive events. If A and B are mutually exclusive, PA or B equals PA plus PB. The earlier dice rolling and spin the spinner settings involved equally likely outcomes. Here's an example that illustrates use of the basic probability rules when the outcomes of a random process are not equally likely. Example, avoiding blue M&M'S, basic probability rules. Problem, Suppose you tear open the corner of a bag of M&M's milk chocolate candies, pour one candy into your hand, and observe the color. According to Mars Inc., the maker of M&M's, the probability model for a bag from its Cleveland factory is color blue, orange, green, yellow, red, brown. Probability 0.2, 0.7, 0.2, 0.5, 0.198, 0.135, 0.1310, 0.124. A. Explain why this is a valid probability model. B. Find the probability that you don't get a blue M&M. C. What's the probability that you get an orange or a brown M&M? Solution. Or A. The probability of each outcome is a number between 0 and 1. The sum of the probabilities is 0.207 plus 0.205 plus 0.198 plus 0.135 plus 0.131 plus 0.124 equals 1. B. P not blue equals 1 minus P. Blue equals 1 minus 0.207 equals 0.793. Using the complement rule, P of AC equals 1 minus P of A. C. P, orange or brown. P, orange, plus P, brown. 0.205 plus 0.124 equals 0.329. Using the addition rule for mutually exclusive events, because an M&M can't be both orange and brown. For part B of the example, we could also use an expanded version of the addition rule for mutually exclusive events. P not blue, P orange or green or yellow or red or brown. P orange plus P green plus P yellow plus P red. P brown. 0.205 plus 0.198 plus 0.135 plus 0.131 plus 0.124 equals 0.793. Using the complement rule is much simpler than adding 5 probabilities together. Check your understanding. Suppose we choose an American adult at random. Define 2 events. A. The person has a cholesterol level of 240 milligrams per deciliter of blood, mg/dl, or above, high cholesterol. B. Psi. The person has a cholesterol level of 200 to less than 240 milligrams per deciliter, borderline high cholesterol. According to the American Heart Association, PA 0.16 and PB 0.29. 1. Explain why events A and B are mutually exclusive. Second, say in plain language what the event A or B is. Then, find P of A or B. Third, let C be the event that the person chosen has a cholesterol level below 200 milligrams per deciliter, normal cholesterol. Find P of C. Two-way tables, probability, and the general addition rule. So far, you have learned how to model random behavior and some basic rules for finding the probability of an event. What if you're interested in finding probabilities involving 2 events that are not mutually exclusive? For instance, a survey of all residents in a large apartment complex reveals that 68% use Facebook, 28% use Instagram, and 25% do both. Suppose we select a resident at random. What's the probability that the person uses Facebook or uses Instagram? There are 2 different uses of the word or in everyday life. In a restaurant, when you are asked if you want soup or salad, the waiter wants you to choose one or the other, but not both. However, when you order coffee and are asked if you want cream or sugar, it's okay to ask for one or the other or both. The same issue arises in statistics. Mutually exclusive events, A and B, cannot both happen at the same time. For such events, A or B means that only event A happens or only event B happens. You can find P of A or B with the addition rule for mutually exclusive events. P of A or B equals P of A plus P of B. How can we find P of A or B when the 2 events are not mutually exclusive? Now we have to deal with the fact that A or B means one or the other or both. For instance, uses Facebook or uses Instagram in this scenario. Just described includes U.S. adults who do both. When you're trying to find probabilities involving two events, like PA or B, a two-way table can display the sample space in a way that makes probability calculations easier. Example: who has pierced ears? Two-way tables and probability. Problem: students in a college statistics class wanted to find out how common it is for young adults to have their ears pierced. They recorded data on two variables, gender and whether or not the student had a pierced ear, for all 178 people in the class. The two-way table summarizes the data. Suppose we choose a student from the class at random. Define event A as getting a male student and event B as getting a student with a pierced ear. A. Find PB. B. Find PA and B. Interpret this value in context. C. Find PA or B. Solution: A. PB. P pierced ear. 103 divided by 178 equals 0.579. B. PA and B. P male and pierced ear. Key 19 178ths. Key ears 0.107. There's about an 11% chance that a randomly selected student from this class is male and has a pierced ear. C, PA or B equals P, male or pierced ear. 71 plus 19 plus 84 divided by 178 equals 174. Divided by 178 equals 0.978. In statistics, or means one or the other or both. So, male or pierced ear includes I, male, but no pierced ear. May pierced ear but not male, and may male and pierced ear. When we found P male and pierced ear in part B of the example, we could have described this as either PA and B or PB and A. Why? Because male and pierced ear describes the same event as pierced ear and male. Likewise, PA or B is the same as PB or A. Don't get so caught up in the notation that you lose sight of what's really happening. Part C of the example reveals an important fact about finding the probability PA or B. We can't use the addition rule for mutually exclusive events unless events A and B have no outcomes in common. In this case, there are 19 outcomes that are shared by events A and B. The students who are male and have a pierced ear. If we did add the probabilities of A and B, we'd get 190 divided by 178 plus 103 divided by 178 equals 193 divided by 178. This is clearly wrong because the probability is bigger than 1. As figure 5.3 illustrates, outcomes common to both events are counted twice when we add the probabilities of these two events. We can fix the double counting problem illustrated in the two-way table by subtracting the probability P, male and pierced ear, from the sum. That is, P male or pierced ear. P male plus P pierced ear, P male and pierced ear. 90 178ths plus 103 178ths minus 19 178ths. Now 174 to 178ths. This result is known as the general addition rule. Definition: general addition rule. If A and B are any two events resulting from some random process, the general addition rule says that PA or B, PA plus PB, PA and B. Sometimes it's easier to label events with letters that relate to the context, as the following example shows. Example: Facebook versus Instagram. General addition rule. Problem: a survey of all residents in a large apartment complex reveals that 68% use Facebook, 28% use Instagram, and 25% do both. Suppose we select a resident at random. What's the probability that the person uses Facebook or uses Instagram? Solution: let event F equals uses Facebook and I equals uses Instagram. PF or IPF, PIPF and I share 0.68 plus 0.28 minus 0.25 equals 0.71. What happens if we use the general addition rule for two mutually exclusive events A and B? In that case, PA and B equals 0, and the formula reduces to PA or B, PA PB, PA and B, PA PB, 0 PAs PB. In other words, the addition rule for mutually exclusive events is just a special case of the general addition rule. You might be wondering if there is also a rule for finding PA and B. There is, but it's not quite as intuitive. Stay tuned for that later. Check your understanding. Yellowstone National Park staff surveyed a random sample of 1,526 winter visitors to the park. They asked each person whether they belonged to an environmental club, like the Sierra Club. Respondents were also asked whether they owned, rented, or had never used a snowmobile. The two-way table summarizes the survey responses. Suppose we choose one of the survey respondents at random. 1. What's the probability that the person is an environmental club member? 2. Find P, not a snowmobile renter. 3. What's P, environmental club member, and not a snowmobile renter? Find the probability that the person is not an environmental club member or is a snowmobile renter. Venn diagrams and probability. We have seen that two-way tables can be used to illustrate the sample space of a random process involving two events. So can Venn diagrams like the one shown in Figure 5.4. Definition: Venn diagram. A Venn diagram consists of one or more circles surrounded by a rectangle. Each circle represents an event. The region inside the rectangle represents the sample space of the random process. In an earlier example, we looked at data from a survey on gender and ear piercings for a large group of college students. The random process was selecting a student in the class at random. Our events of interest were A is male and B has a pierced ear. Here is the two-way table that summarizes the data. The Venn diagram in Figure 5.5 displays the sample space in a slightly different way. There are 4 distinct regions in the Venn diagram. These regions correspond to the 4 non-total cells in the two-way table as follows. Region in Venn diagram in words count. In the intersection of 2 circles, male and pierced ear, 19. Inside circle A, outside circle B, male and no pierced ear, 71. Inside circle B, outside circle A, female and pierced ear, 84. Outside both circles, female and no pierced ear, 4. Because Venn diagrams have uses in other branches of mathematics, some standard vocabulary and notation have been developed that will make our work with Venn diagrams a bit easier. We introduced the complement of an event earlier. In Figure 5.6a, the complement AC contains the outcomes that are not in A. Figure 5.6b shows the event A and B. You can see why this event is also called the intersection of A and B. The corresponding notation is A intersection B. The event A or B is shown in Figure 5.6c. This event is also known as the union of A and B. The corresponding notation is A union B. Definition: intersection union. The event A and B is called the intersection of events A and B. It consists of all outcomes that are common to both events and is denoted A intersection B. The event A or B is called the union of events A and B. It consists of all outcomes that are in event A or event B, or both, and is denoted A union B. With this new notation, we can rewrite the general addition rule in symbols as P of A union B equals P of A plus P of B minus P of A intersection B. This Venn diagram shows why the formula works in the pierced ear example. For mutually exclusive disjoint events, A and B, the joint probability. PAB, because the two events have no outcomes in common. So the corresponding Venn diagram consists of 2 non-overlapping circles. You can see from the figure at left why, in this special case, the general addition rule reduces to PAB, PASPB. Example: Facebook versus Instagram. Venn diagrams and probability. Problem: a survey of all residents in a large apartment complex reveals that 68% use Facebook, 28% use Instagram, and 25% do both. Suppose we select a resident at random. A. Make a Venn diagram to display the sample space of this random process using the events F, uses Facebook and I uses Instagram. B. Find the probability that the person uses neither Facebook nor Instagram. Solution. A. Start with the intersection. P of F. Intersection. I equals 0.25. We know that 68% of residents use Facebook. That figure includes the 25% who also use Instagram. So 68% minus 25% equals 43%, equals 0.43 only use Facebook. We know that 28% of residents use Instagram. That figure includes the 25% who also use Facebook. So 28% minus 25% equals 3%, equals 0.03. A total of 0.43 plus 0.25 plus 0.03 equals 0.71 equals 71% of residents use at least one of Facebook or Instagram. By the complement rule, 1 minus 0.71 equals 0.29 equals 29% use neither Facebook nor Instagram. B, P no Facebook and no Instagram equals 0.29. In the preceding example, the event uses neither Facebook nor Instagram is the complement of the event uses at least one of Facebook or Instagram. To solve part B of the problem, we could have used our answer from the example on page 349 and the complement rule. P, neither Facebook nor Instagram. 1P, at least one of Facebook or Instagram. 1, 0.71, 0.29. As you'll see in section 5.3, the fact that none is the opposite of at least one comes in handy for a variety of probability questions. An alternate solution to the example uses a two-way table. Here's a partially completed table with the information given in the problem statement. Do you see how we can fill in the missing entries? 100% minus 68% equals 32% of residents do not use Facebook. 100% minus 28% equals 72% of residents do not use Instagram. 68% minus 25% equals 43% of residents use Facebook, but do not use Instagram. 28% minus 25% equals 3% of residents use Instagram but do not use Facebook. 32% minus 3% equals 72%, minus 43% equals 29% of residents do not use Facebook and do not use Instagram. The completed table is shown here. We can see the desired probability marked in bold in the table. P, neither Facebook nor Instagram, equals 0.29. Section 5.2, Summary. A probability model describes a random process by listing all possible outcomes in the sample space and giving the probability of each outcome. A valid probability model requires that all possible outcomes have probabilities that add up to 1. An event is a collection of possible outcomes from the sample space. The probability of any event is a number between 0 and 1. The event A or B is known as the union of A and B, denoted. A union B. It consists of all outcomes in event A, event B, or both. The event A and B is known as the intersection of A and B, denoted. A intersect B. It consists of all outcomes that are common to both events. To find the probability that an event occurs, we use some basic rules. Non-certain, if all outcomes in the sample space are equally likely, PA equals the number of outcomes in event A over the total number of outcomes in sample space. Chucker's complement rule. P of AC equals 1 minus P of A, where AC is the complement of event A. That is, the event that A does not happen. General addition rule. For any two events, A and B, PAB, PA, PB, PAB. Addition rule for mutually exclusive events. Events A and B are mutually exclusive, disjoint, if they have no outcomes in common. If A and B are mutually exclusive, P, AB, are PA plus PB. A two-way table or Venn diagram can be used to display the sample space and to help find probabilities for a random process involving two events.